Hey, Advanced Chem students. Today we're going to talk about concentration of solutions. There'll be a little bit of calculations through this, so if you can grab a calculator and a pencil, that would probably be a good idea. If it's sometime in the course of this video, if you need to press pause and go and work one of the problems, that'd be a great idea. Let's just get started. Okay, so when we talk about solution concentration, this is something we haven't actually done yet really in advanced chemistry, but it's a measurement of the amount of solutes in a solvent. So in terms of, say, like a saltwater solution, it would be the amount of salt in an aqueous solution of salt and water. So something that is actually dilute, and if you look at the picture, you can kind of see this. If this were Kool-Aid, right? Something dilute would be very small amount of solute. It would be relatively colorless. Something that was more concentrated would have a larger amount of solute. It would be darker colored. So this over here, whoa, it's moving around. Sorry, guys. If you look at this over here, this would be concentrated over here, and over here, this would be more dilute. And you kind of understand this. This is not difficult to understand, but the concentrated solutions will actually have more molecules present per molecules of solvent, molecules of solute per molecules of salt. We actually do this calculation quite a bit in chemistry, although we haven't done it with you guys yet. We use it in AP Chem all the time, and we used it in our Hess's Law lab when we converted the concentration of the sodium hydroxide to the number of moles of sodium hydroxide that were used for that reaction. So here what we're looking at is the actual formula down at the bottom. So molarity, or our concentration unit, is given as a capital M. And what it stands for is the number of moles of solute divided by the number of liters of solution. So that's the total liters that it's in, its volume, with the number of moles of just the solute on top. So up here it says, a 1 molar solution has 1 mole of solute per 1 liter. Or it has 2 moles of solute per 2 liters. If you just do the division, it will give you the concentration, which would have units of, like it says here, molarity. 0.5 molar NaCl solution would have 0.5 moles of NaCl in 1 liter of total solution. It doesn't mean that it's an entire liter of water necessarily. It might be a little bit less to accommodate for the volume of the sodium chloride. So this can be used in a lot of different ways, but most importantly, and what we use it for, especially in AP chemistry and solution preparation, is changing from one molarity to another. Or for this right here, before we start doing dilutions, we're actually going to talk about how to make a concentration of solution for a given molarity. So for instance, for your lab, for the Hess's Law lab, we needed 0.5 molar solution of NaCl. We needed 0.50 molar, not NaCl, NaOH solution, like this. So for an NaOH solution, we would take actual sodium hydroxide and put it in what we call a volumetric flask. And it's important that you actually know what this thing is called. It is a volumetric flask. And a volumetric flask has an etched line up at the top that will tell you how much you have present, or how much water to get, or how much, I should say, solvent to get to a full 1.0, and it's actually to 4 significant figures, 1.000 liter solution. So what you do is you put in your base. In this case, sodium hydroxide comes as the pellets like we had in the lab. And then you would add water, swishing around while you do it until you get to the etched line here in this last part of the picture. So you fill up to the etched line and then you're finished. You pour it into a bottle, you label the bottle, and you have your solution. These can also be used for diluting substances, which is also something that we'll talk about here in a little bit. So this one says right here, what is the concentration and molarity of a solution made with 80 grams of NaOH and 4.0 liters of solution? So what we really need to know is the formula for molarity is the number of moles of solute divided by the liters of solution. So I need to go solve for my moles of solute. I'm given the liters of solution. I'm given that I have 8, look at me, making some simple errors. Sorry, guys. So it's taking 80.0 grams of NaOH in 1 liter or 4 liters of solution. A lot of times the way I'll work these, especially with AP, is I'll go ahead and put the 40.0 liters, sorry, no, 4 liters. I'm losing it, guys. 4.0 liters of the NaOH solution in the denominator, which basically gives me my density. And then I'm going to convert to moles by taking the molar mass of sodium hydroxide, which is 40.0 grams of NaOH in 1 mole of NaOH, and then I would go and solve. The way the PowerPoint has it is it actually does it in 2 different steps. You go solve for the moles, and you divide by the liters of solution. But this is typically how we do it here. It saves time. So the liters are already in the denominator. My grams are going to cancel with grams, and I'm left with my units, or my ending units, being moles over liters. So if I show you kind of answer here, it would actually be a 2 molar solution, which is pretty easy to calculate. This would have 3 significant figures, of course, because I've got, 80.0 on top and 40.0 on the bottom. Well, this would have 3 significant figures for the moles, but actually be 2 total because the denominator here is 4.0 liters. Pretty easy calculation, just showing you how to calculate what the actual molarity would be. But if you wanted to prepare the solution, you would actually take 80 grams of that sodium hydroxide solution, put into, in this case, a 4-liter volumetric flask, and add up to the etched line. Even though that sounds kind of bogus, you're allowed to kind of make up glassware as you go along. Kind of one of the cool things for it. Oh, we got skipped around here. My apologies about this. Anyway, okay, so how would you make a 500 milliliter solution of 6 molar NaOH? So in this case, you actually are going to start with your 500 milliliters. Let's see, let me get my pen out here. 500.0 milliliters of the solution that we want. Of course, it's in moles per liter, so what we're going to do is we're going to transfer that to liters by changing our milliliters to liters. And I want a 6 molar solution, so what I'm going to do is use the molarity in moles per liter as a conversion factor here. So 6.00 moles of the NaOH solution is 1 liter. And that came from right here. This 6 molar solution is this 6.00 moles per liter. And then if I want to find out how many grams I need, because you can't really measure moles on a balance. You can measure grams, you can measure mass. 1 mole of NaOH, if I use my molar mass from the previous equation, is 40.00 grams, or 40... Oh, I did it again. Some issues with my decimal places here. 40.0 grams of NaOH. What I end up getting here is 120 point... That's not 0.0 because there's only 3 significant figures in 6.00. So 120 grams of NaOH. So what I would do is I'd take out a balance. I'd measure, because this question says, how would you make it? So in order to how I would make it, I would take 120 grams of this solution, mass it on a balance, and then I'd put it in a 500 milliliter volumetric flask, and I would add, I'm not sure what happened there. I would add water until I got to the etched line. Or you could say add distilled water to the etched line, which even be better. So down there on the bottom is the same kind of deal. Mass 120 grams of NaOH, put it into a 500 milliliter volumetric flask, and add to a 500 milliliters total of solution. You guys are going to be asked to write directions for how to do these, so you need to know the vocabulary of these devices that we use. So you need to know volumetric flask. You need to say, and even though it doesn't say here, it says add enough water. That would be sufficient. But I would say add water to the etched line. Now, I wish we were in class today to kind of show you what these things look like, but if you remember to ask us later, maybe we'll show you one of them. They look just like the picture with an etched line on top. Pretty cool. We use them all the time. So dilutions is what I kind of was hinting at before, but we use this a lot for dilutions. So when we're prepping chemicals, we have dilutions on the shelf, or we don't have dilutions on the shelf. We have stock chemicals on the shelf that are in certain concentrations. Some of them are really concentrated, meaning like 6 or 10 or even 12 or 17 molar. And we have to make something that's more dilute for a lab that we're using, say 0.1 or 1 molar or something like that. So what we use is this formula here, and this formula is a dilution formula. This is kind of strange that it's written this way, but usually we write M1V1 equal to M2V2, where the initial molarity of our stock solution is given as M1, and the volume of that stock solution that you need is usually what you solve for, is V1, And then M2 is what you're looking for in concentration and what volume of that concentration you want. This formula only works for dilution of a solution. So this right here, this formula, only dilutions. There are other formulas that we use for some acid-base reactions that we'll talk about later. Don't use this for reactions. This is only for changing a solution to another concentration, changing one concentration to another. So what you would be doing is you would be changing like a sulfuric acid solution to a more dilute sulfuric acid solution. It's not reaction chemistry. It's just changing how many moles of something you have per unit of volume to a new concentration. Let me get back to where we were. So let's do a quick example. So it says, for a lab, we need 500 milliliters of 6 molar hydrochloric acid. Concentrated HCl is 12 molar. How do we make up the solution? Okay, so the formula that we're going to use is M1V1, M2V2. We're not doing some kind of reaction. We're just taking HCl, hydrochloric acid, and changing from 12 molar, what we're given here, to 6 molar. Now notice that I'm given the volume and concentration of what I need, and I don't know how much of the concentrated solution that I want. So what I would do is I would actually list your variables. And you can call either one of them number 1 or number 2. It doesn't really matter. I prefer to call the more concentrated one, our stock solution, the number 1, but like I said, it doesn't really matter. What we're looking for is what concentration we need of the 12 molar to make a 6.00 molar solution with a total volume of 500.0 milliliters. Yeah, there we go. Now, because we're actually using volume on both sides of the equation, we don't really have to change it to liters. You could change it to 0.5000 liters if you wanted to, but you don't have to do that. You can leave it as is. So I would take my 12.0 for my concentration. Excuse me. I'm solving for that volume that I need of the concentrated solution. What I want to make is the 6.00, and how much of it do I need? Running out of room. I need 500 milliliters of it. What I'll end up getting in my answer here is a certain number of milliliters. I think this volume ends up being, let's see, 250 milliliters. So the answer here for how much I would need would be 250 milliliters. That isn't what they asked in this question, though. Be careful. It says, how do we make this solution? Well, you make this solution by taking 250 milliliters of the concentrated acid, placing it in a volumetric flask, and then filling to the etched line using a 500 milliliter volumetric flask. The hiccup with acids is we always add acid to water, okay? It's a safety thing. We did it at the very beginning of the year. You may remember, you may not, but we always add acid to water. It goes alphabetically, A to W, or if you like A and W root beer, maybe that'll help. But we add acid to water always. So if you're going to actually write this correctly, let me show you the next slide. You wouldn't describe it as 250 milliliters and then add to the etch line of 500 like you would with a solid. You actually have to add some distilled water first. So add some distilled water. It doesn't really matter how much, but you want to get close to the amount that you're going to add. You want to add a little bit less. But you would put in, say, 225 mils or so into the volumetric flask. Add your required amount that you got from your calculation here, the 250 mils of 12 molar, and then top it off to make your 6 molar solution. And you add enough water there basically to make the 500 milliliters of solution. It's tricky with the acids, but anything that's concentrated, you want to put some water in first, add it till you're close, and then top it off with water at the end. If it's a solid that you're adding, you don't necessarily have to do that. There are some tricky solids, but we're not really going to get into that with you guys at this level. There are other ways that different sciences actually calculate concentration, and chemistry will use molarity almost exclusively. Sometimes we'll use percents, and there's a few different ways to calculate percent. This first one is percent volume by volume. So what you would do is you take the volume of your solute, meaning these are two liquids you're putting together, volume of your solute divided by the total volume of your solution. And so like rubbing alcohol, 70% isopropyl alcohol by volume. So what you would do is you would take that means that it's, 70 milliliters of isopropyl alcohol for 100 milliliters total solution. To find out how many milliliters you would need of each of these, you can just plug it into the equation and solve. And I'll just put it to you down here on the bottom. It's just basically a ratio. So if it's 70 milliliters per 100 milliliters, you just solve for the number of milliliters you need for 250. Simple calculations for percents. Like I said, in chemistry, we're really not going to use percents. We will use concentration instead, but we do need you guys to see how to make these. Biology does a lot of their concentrations and percentages. They're easier to calculate. You don't have to use any molar mass, but they're not quite as accurate. Sorry about that, guys. So another way to do it, and we do this sometimes in chemistry, is the mass of the solute per volume of solution. It's very similar to doing molarity, except you just use mass. So like a 25% solution of sodium chloride is something, common, say, in a biological experiment. You would just have 25 grams of the sodium chloride solution in, say, 100 milliliters of water. So if you were to, like here on this bottom calculation, write directions for preparing 525 milliliters of aqueous NaCl solution, and it says that the percentage is 6.8 percent mass volume. Now you do have to say whether that percent is mass volume or volume, and they say here it's mass volume. I would take my 6.80 grams in 100 milliliters of solution. That's the mass volume, but I want to change it to, say, I need 525 milliliters of that solution. So I would use as my final 525 milliliters and solve for that mass that I would need to do that. Simple ratio, you end up solving. When we get back here, the value is actually 35.7. Should have let you guys do some of these. I apologize. But if you're doing this at home and you want to stop and kind of go and do it on your own, knock yourself out. All right, so yeah, that's how you calculate mass volume. So there we go. This is very common, actually, in biological laboratories. They use percents all the time. Like I said, it's just a little bit easier to calculate. If you want to pause and look at the joke, knock yourself out. I'm moving on. Okay, so let's do a couple of examples here. So what volume of 0.246 molar nitric acid solution is required to react completely with 38.6 milliliters of 0.0515 molar barium hydroxide? This is called solution stoichiometry. So in order to do this, and this balanced equation is tragic in this PowerPoint, I apologize, but this 2 is actually the coefficient. This 3, I have no idea what that 2 is not a coefficient. My mistake. This should say 2 here. This should say HNO3 here. And the barium nitrate should have, subscript there, and water, subscript there. My apologies, guys. Okay, so anyway, in solution stoichiometry, what you're going to try to do is find the number of moles of one substance you have, and then use that mole-to-mole ratio to find the other substance. So in this particular case, what we're doing is we are changing from barium hydroxide, which we know both parts of. We know both the volume right here and the concentration of barium hydroxide. In that way, by using both of those, we can find the number of moles. Then we can use our coefficients. The coefficient of barium hydroxide is 1. The coefficient of the nitric acid, of course, is 2. We can use that 1-to-2 ratio to find out how much nitric acid we need. So let me go through and show you how to do this. When you start these problems, a lot of kids just get lost in how to start. Look for the one that they gave you both numbers. If they give you milliliters and molarity of the barium hydroxide, that's usually what you're going to start with. Now they gave us, actually that's always what you're going to start with, 38.6 milliliters of the BaOH2, and I anticipate I'm going to run out of room here. I need to change my milliliters to liters. And then once I have liters, if I put my liters down here in the bottom, excuse me, I can change that to moles by using the molarity. Remember, the molarity is the number of moles per liter. So if I look up at the top, they did give me the concentration of barium hydroxide. It's 0.0515 per 1 liter. And I'll go ahead and write this. Barium hydroxide. Now, what I want to do is change that moles of barium hydroxide. Now, if I look, my milliliters are canceling, my liters are canceling. I'm left with moles. I can put moles of the barium hydroxide here on the bottom. And on top, I can change from barium hydroxide. What am I doing? That's barium nitrate tolid. You're losing your mind. I can change my barium hydroxide to my nitric acid. Sorry, it's over here on the left. Barium hydroxide to nitric acid using that 1:2 ratio. So 1 mole of barium hydroxide is 2 moles of the HNO3. Now at that point, I have moles of HNO3. What it's asking for is the volume of a certain concentration of nitric acid. So I kind of ran out of room here, but the moles of barium hydroxide are canceling. What I'm left at that point with is moles of HNO3. And using my molarity as moles over liters, I can change that by using my 0.246 moles of HNO3 is 1 liter of HNO3. Now I could change this back to milliliters. I guess I'll go ahead and do it. Why not? But they're going to end up canceling out anyway. 1 liter is 1,000 mils. And that would give me my answer. I know that's a mess. I'm going to show you guys a prettier version. So there you go. There's your prettier version, but it's done the same way. Take your volume and change using your molarity to moles. Change then using your balanced equation, using your multimole ratio to the moles of what you want to solve for. And then use molarity again to change back to liters of the substance that you're looking for, which in this case was the nitric acid. So what you would say is I need, 16.2 milliliters of 0.246 molar nitric acid required to react completely with that barium hydroxide. This is a frequent question in AP Chem. Well, look at this. We don't even have a yield symbol. Frequent question in AP Chemistry. So if you guys need some help, ask them. They can do this kind of stuff in their sleep. Let's do one more example, and then we'll call it quits. So it says calculate the number of grams of carbon dioxide. So in this case, we're looking for... Oh, look at that equation. This is not working well, but we can do that. We'll write the H2O over here. There we go. Good enough. So potassium hydroxide and carbon dioxide react to form the potassium carbonate in water. It says calculate the number of grams of CO2 that can react with a volume and a concentration of potassium hydroxide according to this equation, or the reaction below. I want you guys to go ahead and try this. It's done very similar to the one above, but instead of going to milliliters, we're going to actually go to grams. Go ahead and hit pause and give this one a shot, see if you can get to the grams, and I'll come back on in a minute or so and let you take a look. I'll actually walk you through it. Okay, so I'm going to assume you hit pause and you're back now. What I said before was take the one that you have the 2 numbers of. So hopefully you took the 135 mils of the 0.357 molar potassium hydroxide solution and start with that. So I'm going to start over here with my 135 milliliters of the KOH. I'm going to convert the milliliters to liters because concentration is actually in liters and not milliliters. And if I do that, I can then use my concentration that was given. So it is moles per liter, so I'm going to write 0.357 moles of KOH per liter of KOH. At that point, I have moles. So then I can use, it says calculate the number of grams of CO2. I can change from my potassium hydroxide to my CO2 using a mole to mole ratio. From that balanced equation, there are 2 moles of potassium hydroxide for every 1 mole of CO2. At that point, I have moles of CO2, but they didn't ask me. It didn't say calculate the number of moles of CO2. It actually said calculate the grams. So it's doing it again. My bad. Sorry, guys. Put mole down here and then calculate the molar mass of CO2. The molar mass of CO2 is 44.01. And that would end up giving you grams of CO2. So a little bit, hopefully you set it up the same way. I'm not sure. Let me show you. We'll go back to mine. What was 1.06? So 1.06 grams, I think that's right. 1.06 grams of CO2 is actually your answer here. So in solution stoichiometry, it's done just like we did stoic in December. But using concentration as a conversion factor, use it in terms of moles per liter. So get to the number of moles of the substance that they gave you, and then do your mole-to-mole ratio, and then transfer to whatever it is you're looking for. I can guarantee you we're going to ask you to solve for liters of the other substance. We're going to ask you to solve for milliliters, possibly grams like this one, or even molecules. Anyway, that concludes this unit. I know there's a little bit of math in here. Do review over your calculations that you guys had when we changed phases. We did phase changes. You guys will get the same units and same units, listen to me. The same givens that you had on the last test. So the specific heat of water, molar heat of fusion, molar heat of vaporization. You may want to review those before we do the exam. Okay? You guys have a great weekend. Version with the answer. Tragically on here, this is a mess. I'm glad I'll go back. That's actually not that pretty. PDF didn't work out for every answer, so I don't have to get out my calculator. One more check. Sorry.